Hello. Okay, this screencast is going to cover section 11.3. So if you came to class on Monday, you don't have to watch almost hardly any of this. I'll tell you where to fast forward to get to the end for stuff I did not get to on Monday or on Wednesday. This is covering section 11.3, heat in changes of state. So what happens? Could you explain thermodynamically what happens if you place an ice cube on a table in a warm room? How would you explain that from a thermodynamic standpoint? And in this, before you could even explain it, you have to define a system and surroundings now. So is the table the system? Or is the ice cube the system? Well, for the sake of our discussion, the ice cube is going to be the system, and the table and the air around the ice cube would be the surroundings. So we would say the ice absorbs the heat from its surroundings and begins to melt. Now, the ice and water are going to remain at 0 degrees Celsius until all of the ice has melted. And the temperature of this system will only increase after all the ice has melted. Now, like ice cubes, all solids absorb heat as they melt to become liquids. And if you place a pat of solid butter on a pan, it's going to melt as it absorbs heat from the pan, and it will become a liquid. And solid iron also melts as it absorbs heat from a furnace to the point where it even becomes pourable. Okay, so the heat absorbed by 1 mole of a substance in melting from a solid to a liquid state at constant temperature is called the molar heat of fusion. And remember what 1 mole is. 1 mole is 6.02 times 10 to the 23rd particles, or representative particles, or ions, or atoms, or molecules. That's what 1 mole of a substance is. So the amount of heat absorbed by that 1 mole of substance going from a solid to a liquid state at constant temperature, again, is the molar heat of fusion, and you see the symbol for it there. So we know that when ice absorbs heat from its surroundings, it becomes liquid water. By contrast, when water releases heat, so water's not absorbing any heat anymore, water is releasing heat to its surroundings, it becomes ice. So remember in class I talked about this idea of ice cubes in an ice cube tray. So what you do is you get your ice cube tray, you go to the tap and fill it up with tap water, and the tap water is going to be about 70 degrees Fahrenheit. You then take the ice cube tray with the water in it and you stick it in the freezer. So what happens if you are the water in that ice cube tray? Well, you are becoming cooler, which means that you are dumping your own heat into the surroundings, okay? So you're releasing heat to the surroundings, and then you ultimately become ice. Now, this also carries over if we're getting back to our discussion of iron. So when you pour liquid iron into a mold, the liquid iron cools. It is releasing its heat to the surroundings in order to form a solid. And if you look at that image there, you see that the hot iron, if you look around the perimeter of that mold, we see that the iron is solidifying there first because it's transferring all its heat to the mold there. Now, the heat released by 1 mole of a substance in forming a solid from its liquid state at constant temperature is called the molar heat of solidification. It's the opposite of the molar heat of fusion. It goes in the opposite direction. So the quantity of heat absorbed by a melting solid is exactly the same as the quantity of heat released when that same liquid solidifies. And we can show this relationship as follows. Note that the molar heat of fusion is the same as the enthalpy of solidification there, but it's just it's the same value. It's just going to be a different sign. Okay, and if you look here, if you look at the molar heat of fusion, when water goes from an ice cube state to a liquid, it absorbs 6.01 kilojoules per mole. And by contrast, when liquid water goes from its liquid state to a solid state, and remember in this case it's releasing heat, it is also 6.01 kilojoules per mole, but in this case it's releasing heat. And we show that releasing of heat being exothermic from the water's point of view, we show that as a negative value there. So forgive me while I take my shoes off. All right, so another way to show this is through this there. Look at that little equation I wrote. If you look at solid water going to liquid water, the top arrow is showing the reaction going from left to right. Note that the molar heat of fusion or enthalpy of fusion is 6.01 kilojoules per mole. If we go from liquid water to solid water, we're going in the reverse from right to left. We see that there's a molar heat of solidification, and water is releasing heat to the surroundings, negative 6.01 kilojoules per mole. So I just restated this up at the top of the slide there. And from this, it should be apparent that enthalpy changes accompany changes in heat. Okay, so in this case here, what we've been discussing, no chemical reaction has been going on. We're just watching matter go from a solid to a liquid phase or from a liquid to a solid phase. Well, these changes of phase have heat changes that go with them. So fusion, which is another word for melting in this application, fusion and vaporization are endothermic processes, and solidification and condensation are exothermic processes. If you look in your textbook at table 11.5 on page 308, it provides you some values for many substances, and your table is going to look a little bit different than mine. I could not find your exact table on the internet, but we're going to use this table to solve some problems coming up. So you want to make sure you're pretty comfortable using this table. We're going to use this table in solving this practice problem. How many grams of ice at 0 degrees Celsius and at atmospheric pressure, 101.3 kilopascals, could be melted by the addition of 0.400 kilojoules of heat? So how would you solve this problem? Well, the first thing I would do is where I would in my mind see this process. And I'm realizing that, oh, I'm looking at how many grams I'm going from ice, from the solid state to the liquid state. So I know that there's a certain value, a certain enthalpy value that I'm going to look for on a table. And it's for water. So I'm going to look to table 11.5 to first find the molar heat of fusion. And if I look down here under water and I go to the section here under the enthalpy of fusion, I see that I'm going to use the value of 6.01 kilojoules per mole. And I might write that in the margin of my problem. Okay, so we know that the delta H of fusion is 6.01 kilojoules per mole. And if I start off with the value, I'm being told that I have 400 kilojoules of heat to burn. And I want to know how many grams of ice can I melt with that much heat. So I'm going to, since I see kilojoules and moles, I'm going to use the molar heat of fusion. I'm going to use that value right here to convert into moles of ice. And then if you see this 18.0 grams of ice per 1 mole of ice, I'm just using the molar, what do you call it, the molar mass is all I'm using. We learned how to calculate this about 4 chapters ago. And if I set this problem up, I make sure all my units cancel out okay. And I see I end up with 1.20 grams of ice. So you need to ask yourself, does this answer make sense? Well, yeah, it kind of does. because they're asking me how many grams of ice can I melt by the addition of heat. Okay. Problem number 21 is similar. How many kilojoules of heat, but in this case, they're asking me to solve for how many kilojoules of heat. So the question is, how many kilojoules of heat are required to melt a 10-gram popsicle at 0 degrees Celsius and at atmospheric pressure? Assume the popsicle has the same molar mass and heat capacity as water. So what I'm going to do, first thing is I'm going to go to my table again, and I'm going to remind myself of the molar heat of fusion for water. And I know from the table that it's 6.01 kilojoules per mole. Well, then I'm going to insert this in my problem. They're telling me that I have 10.0 grams of ice. And the question is, how much heat do you need to melt that? So I start with 10.0 grams of ice. I then got to get that, I've got to convert the grams of ice into moles of ice. So that my stoichiometric relationship, so everything works out okay. So I set the problem up like this. 10 grams of ice times 1 mole of ice over 18.0 grams of ice times the molar heat of fusion ratio there. And I set everything up so units cancel, and I'm left only with kilojoules of heat. And that's what I wanted to solve for. Now we're going to move on to a little bit different. We're going to carry this whole idea a little bit further. When liquid absorbs still more heat, so we went from our ice to a liquid. So now when liquid absorbs still more heat, and at their boiling point, liquids become vapors. Okay? And the vaporization of a liquid through boiling or evaporation cools the environment around the liquid as heat flows from the surroundings to the liquid. Now this seemed really indeed counterintuitive, because how many times do we, well, I hope not too many times, but for me it's been enough times, and I guess I'm not learning, that when I lift the lid off a pan and a whole bunch of steam comes out, and boy, that steam is hot, and I'm thinking, man, that's a system that's releasing heat, not absorbing heat. But in fact, it is a system that is endothermic. And let me qualify this statement. Consider the heat of a flame under a pot. And because the pot is absorbing some of the heat from that flame, the flame is in fact a little bit cooler than if there were no pot at all sitting on top of that flame. Okay, in class we talked about this idea. If you set up 2 burners here, 1 burner on each side, and you turn them both on to the exact same heat, then you measured their temperature with a thermometer, with a probe. And let's say that on the right side of the burner, on the right burner, you get a pan of water and you set it on there, and then you let the water start boiling and then pull that pan off right away, and then measure the temperature of that burner that had the pot on it, and compare it to the burner that had no pot on it, you would see that the burner that had the pot on it is indeed cooler because it transferred its heat to the pot of water. Okay? So the amount of heat necessary to vaporize 1 mole of a given liquid is called its molar heat of vaporization. And water's molar heat of vaporization is 40.7 kilojoules per mole. And in order to vaporize 1 mole of water in its liquid state, 40.7 kilojoules of energy is necessary. And we show there, we show in that equation there, the phase of water going from its liquid state to its gaseous state. And we see that in that case, it's going to absorb 40.7 kilojoules per mole of energy. Now, diethyl ether is a low boiling point liquid. It has a boiling point of 34.6 degrees Celsius. By comparison, water has a boiling point of 100 degrees Celsius. So diethyl ether is about 1/3 of the boiling point of water. And diethyl ether, just used to be called ether, was formerly used as an anesthetic. So if you poured, if you had some of this, I'd have to wonder why. Why do you have diethyl ether in your house? But if you did, if you poured some in a beaker on a warm, humid day, the ether will absorb the heat from the beaker walls and evaporate very quickly. And if the beaker loses enough heat, then the water vapor in the air will actually condense and freeze on the beaker walls. So the beaker will actually feel cool. And so we know that the molar heat of vaporization for diethyl ether is 15.7 kilojoules per mole, quite a bit less than that for water at 40.7 kilojoules per mole. So the question I posed to you, and if you were in class Monday, you already know it, but when vaporizing, is this an endothermic or an exothermic reaction? I'll give you 3 seconds to guess. 3, 2, 1. Da 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 da. It's an endothermic. It's not a reaction. It's a process. It's an endothermic process. So we just talked about vaporization. And vaporization, just remember, is when liquid goes to steam. Now we're going to look at the reverse of that, when steam condenses back to liquid. So condensation is the exact opposite of vaporization. So the amount of heat released, this is exothermic. When 1 mole of vapor condenses is called its molar heat of condensation. We can show this relationship as follows. The molar heat of vaporization, it has the same value number-wise as the molar heat of condensation. Is just opposite. It's just opposite in direction. So if you look at water going from its liquid state to its gaseous state, we see that the molar heat of vaporization is 40.7 kilojoules per mole. But if we then look at water going from its gas phase to its liquid phase, we see that the molar heat of condensation is negative 40.7 kilojoules per mole. Okay, so now let's do a practice problem. How much heat is in kilojoules? Report this in kilojoules. Is absorbed when 63.7 grams of water at its liquid state and at 100 degrees Celsius is converted to steam, still at 100 degrees Celsius. So you're going to look to the table 11.5 to first find the molar heat of vaporization for water. And there's your table. So you're going to go over to where water is. You're going to go all the way over here. Notice that this label here is the molar heat of vaporization reported in kilojoules per mole. And for water, it's 40.7. So we're going to write that little value in our margin as we're solving this problem. And then we're going to go from 63.7 grams of water. We're going to convert it to moles. And remember, the molar mass of water is 18 grams per mole. And then we're going to do one more step and convert those moles to kilojoules. And the relationships look like this on your slide. So 63.7 grams of water times 1 mole of water over 18 grams, there's its molar mass, times the molar heat of vaporization of water. And I set up that ratio so that all of my units would cancel, and I would end up only with kilojoules of energy. Okay. So here's another practice problem. How many kilojoules of heat are absorbed when 0.46 grams of chloroethane vaporizes at its boiling point? So can you guys imagine? And we talked in one class about what a tiny quantity 0.46 grams is. But imagine a little tiny beaker with a little bit of chloroethane. Now this stuff is even more volatile. It wants to evaporate than ether is, because it's got a really super low boiling point. So can you see this happening? Can you see the ether in the beaker just evaporating? Well, the question is, how many kilojoules of heat are absorbed by that system when this happens? So the problem tells us that the molar heat of vaporization of chloroethane is 26.4 kilojoules per mole. And if I set this problem up the right way, I start with 0.46 grams of chloroethane. I multiply it times its molar mass, and then I multiply that times the molar heat of vaporization ratio, making sure that I set the problem up so all the units cancel out, and I'm left only with units of joules, or kilojoules in our case. All right, so there's one of these heating and cooling curves in your textbook in this chapter. And what I want you to look at is, I want you to notice, look at what is plotted on the x-axis. The x-axis reflects heat added. This reflects us turning on a Bunsen burner or turning on a stove, okay, and adding more heat to something. And along the y-axis, it's showing the temperature of your substance. Now, in this case, this is a heating and cooling curve for water. Do you notice that as heat is added, that you don't have a perfect, whatever, you don't have a perfect straight line relationship when that happens? You notice that the line kind of zigzags a little bit, okay? It's a broken line, and there's some reasons for that. And what I want you to notice is that temperature remains constant during melting and vaporization. Let's follow this line here. Let's start at the origin. So at the origin here of negative 40 degrees Celsius, I add a little bit of heat to water, and the temperature immediately goes up as it's turning into a liquid. Okay, this is as the ice cube is melting. Its temperature is going up, and then it hits 0 degrees Celsius, which is the melting point of water. And once the ice cube has completely melted, I can keep, let me activate my cursor, I can keep adding heat to that sample of water, and it's just not going to increase in temperature for a while. But there comes a point then when, as heat is added, then, when this actually changed, when it's in its liquid phase, it's actually going to start completely, the temperature is going to start increasing. And there comes a point where it's in between that phase of gas and a liquid, and while we're waiting for all the liquid to vaporize, again, the temperature is just not going up that quickly. And then once everything becomes a gas, the temperature spikes in the system. So kind of an unusual trend there. And note the two areas that during the, that the temperature remains constant during melting and during vaporization. So as long as there's some motion going on with the particles, as long as the ice is still converting, into the liquid, the temperature is going to remain constant. And it's not going to start budging until all the ice is a liquid, and then we're adding more heat to the system. So also note, I have two double-sided arrows on here. Also note that it takes much more energy to vaporize liquid water than it does to melt the same mass of ice. So look at how much energy it takes there to vaporize water completely. It takes quite a bit, much more so than it takes to melt the same mass of ice. And that kind of makes sense when you look at, when you look at the values for the molar heat of fusion, going from liquid to going from solid to liquid for water is 6.01 kilojoules per mole. Not that much, but going then from liquid to gas, when we look at the molar heat of vaporization, it's 40.7 kilojoules per mole. It's a lot harder. What this tells us is it's a lot harder to vaporize something than just to melt something. We didn't get to this, but this needs to be covered. Heat changes, and this is this notion of heat of solution. Heat changes also occur when a solute dissolves in a solvent. Now, I'm hoping on Monday to bring a demonstration in of this very thing. The heat change caused by the dissolution of 1 mole of substance is the molar heat of solution. And as this is a great example, when 1 mole of sodium hydroxide is dissolved in water, the solution becomes so hot it steams. 445.1 kilojoules of heat is released. And I can tell you, before looking at this, I can tell you that when I've dissolved sodium hydroxide in water to make lye solution for soap, boy, I mean, my beaker gets hot to the touch. Gets really, really hot. And all I'm doing is dissolving sodium hydroxide. Well, this whole idea, and again, these heat of solutions happen in the case of sodium hydroxide because the ions are breaking apart. It just releases a lot of heat. This notion of heat of solution has an application in the development of hot packs. And as an example, when you have a hot pack, you have 2 chemicals that are in separate pouches. They're separated from one another. Okay? And then what you do is you break the pouch so that the pouches are then broken open, and then the 2 chemicals mix together, and then you have a heat of solution phenomenon. Heat is released. And in these hot packs, they mix calcium chloride and water, which produces the heat characteristic of an exothermic reaction. And I show here a little chemical equation where calcium chloride, when dissolved in water, forms calcium ions and chloride ions. And look at the stoichiometric relationship there. And the heat of solution, the molar heat of solution, is negative 82.8 kilojoules per mole. So that's not a bad amount of heat. That's a pretty good amount of heat. Now, we're going to look at this on the opposite side. We're going to look at this when it occurs for an endothermic process. The dissolution of ammonium nitrate is an endothermic process. And guess what? This has its application in cold packs. Okay, when ammonium nitrate dissolves in water, the solution becomes so cold that frost may form on the outside of the container. So heat is released from the water. Okay, this again sounds a little bizarre. Take a look at this. We have ammonium nitrate. We're dissolving it in water so that it forms ammonium ions and nitrate ions. And in this, it becomes an endothermic reaction. And we show here the molar heat of solution, in this case, is 25.7 kilojoules per mole. Okay, so an application, how do we solve a problem knowing this now? We would ask how much heat in kilojoules is released when 0.677 moles of sodium hydroxide is dissolved in water. And we know from the textbook that for every 1 mole of sodium hydroxide dissolved, we know that 44.1 kilojoules of heat is released. And if I then, and again, you often will have tables that will tell you this stuff as well. So I set the problem up here, 0.677 moles of sodium hydroxide, and then I multiply it times that ratio, the molar heat of solution. And then I end up with just how much heat is released when I dissolve 0.677 moles of sodium hydroxide in water. Here's another problem. This is the endothermic side of it now. How many moles of ammonium nitrate must be dissolved in water so that 88.0 kilojoules of heat is released from the water? So we know from the text on page 312 that 25.7 kilojoules of heat is released when 1 mole of ammonium nitrate is dissolved. And again, I just set this problem up starting off with, it's like someone gave me 88 kilojoules of heat. And now they're saying, if you have that much heat, how many moles of ammonium nitrate are you going to have to dissolve then? And in this case here, I got 3.42 moles of ammonium nitrate. So that's all I have for this section of the textbook. On Monday, I'm going to go ahead and do section 11.4. I don't want to do that on a screencast because I don't think this is any harder than the other 3 sections, but I want to take some time in class to discuss this. So guess what? We're off syllabus, guys. I'm really sorry about that. You all have a great weekend. Don't forget to bring in your quiz, your take-home quiz. Make sure your parents proctor it, and bring in your lab. Make sure you bring in your lab, and I'll run the reaction tonight and send you some data for burning the cracker, okay? We'll see y'all later. Have a great weekend.